Hello, hello. This is just going to be the third video into the Phase 3 binary bomb. This application binary is from Xeno's Open Security Training 2, so I'm just going to be going through reverse engineering. And I'm also this time going to actually copy and paste the assembly here in another notepad. So I'll just have this for the assembly I'm looking at, as well as the registers. That way it will be a little bit easier to see what exactly I'm referring to instead of just looking at all these different screens on the debugger. And then also just want to shout out to this channel, Dr. Gorgon, who goes through the binary bomb. And it's a little bit different on the phases, but this phase really was the same, I think, and it really helped me understand exactly what I had to do, because I was kind of stuck on this phase. I wasn't really understanding what exactly I had to look for. And so we're just going to get right into it. And for this, I'm just going to put like the logic that I understand. Okay, and so we're just going to restart this. Going back from the beginning, we're going to reload it. Reload the symbols. We're going to just break point at main. Just go ahead. And we already figured out the solution for the other two problems. I am just a renegade hockey mom. This one is the 2 to the power. Now, before we get into it, I didn't do this last time, but I think we already can see, at least from what we read here, is that the assembly looks like this so far. So we have the print line, we have print here, we have read line, which is where we are right now in terms of the execution. So it's looking for some input here. And so... And we're just skipping all the stuff beforehand because this is all the stuff that was in phase 1 and phase 2. So if you want to get more information, you just go right through that video. And so from what I understand here, this got printed off on that message. So that's number 2, keep going. So let's just write that here. So the logic would be print the message, print message, then we're going to next line it from this assembly here, or read line. Read line here, and so read this line. And what's interesting here is now we have these phases, phase 3 and phase diffused. And so just like before, we had the phase 3, and then we had phase diffused. And we're assuming it's going through the same pattern. It's going to go into that function, and then if everything is fine, it's just going to go in phase diffused. And so before we even scan here, let's just look into phase 3. And so we can use the disassembler, and we can actually go in and analyze the entire code. And we notice that some code may be missing. So let's just look at what we have here so far. Before we're even actually looking into any of the code itself, a lot of the code here, like we said before, is just pushing the stack, allocating specific memory. So some things we want to really look out for are calls. We have a call here, call scanf here. So this is kind of important. We'll just add some space here just to note it. And when we go in through the Wind debugger, it's going to kind of create these sections, which can be helpful, cannot be helpful, but they're separated by these jumps. So every time you see a jump here, jump here, jump here, it's going to segment. It's going to kind of be helpful. I guess I haven't really done a lot of work on terms of this branching. So you can branch when you go here into the debugger, and I think it can kind of create this tree to kind of show you the specific logic movement. I haven't done anything like that. I've just kind of read through this code, but you can also look here at the 07E, and it kind of can tell you here that it's going to jump to this part as well. That can be useful as well. So let's see, scanf here. And so we're noticing a lot of jumps here. Jump, jump. And okay. And this is the last bit of the code. Okay. So the very first thing is we have to figure out what is the scanf here. Scanf compare to 2, I guess. EAX put this return value from the scanf into this memory. If this doesn't match 2, then if this is greater than or equal to this, jump here, else you're going to explode. And so we can kind of see, at least from what we know here, like we had before, the input. It's like string input equals, and then input here is going to go into scanf, take our input. It's probably going to take some value here. If not, if it doesn't match that, if scanf is not equal to 2, I think, then just if it's greater than or equal to this, so if it's less than 2, explode. Explode bomb. And so, yeah, jump compare greater than or equal to 2. Just for our sake, let's just slowly go into this one as well. So I'm just gonna go through. Oh, I didn't step through. Sorry. Let me just go here and put just this here, and let's just step to the code here. And let's just look at those values for scanf. Scanf, just from my memory, I think it takes like 2 strings, or at least like, no. It does 6 strings, but I'm reading the wrong pieces of memory. RCX, RDX. Okay. Okay, I see. So what I did was I just looked into the first 2 arguments of scanf here. And again, in the debugger, I pulled these 2 values here. And you can see where I'm at. I'm actually right here at scanf at the bottom. So I'm right here at this call. Before I call this scanf, I wanted to see what is the first 2 arguments. So this is the first argument. This is the second argument. And we're going by the registers RCX, RDX. Scanf, I think this is for the strings. Yeah. And so this one is the input. This one is formatting. And so just very quickly, I was able to at least determine that. And so for logic, this input has to be %D, %D. And so that means that whatever I put here was wrong anyway. It needs to be 2 numbers. So we're just going to continue because this is wrong. As you can tell, we get here. and then it's just going to explode. Boom, the bomb has exploded up. So we're just going to restart. At least we know from this part some crucial information from here. So inside of, this is the code for phase 3. While running through here, go here, call the scanf, look for the input, make sure it matches the formatting. If it doesn't match that formatting, through this, move the return value into this memory. If it doesn't match 2, I'm guessing if it's not like 2 values or it didn't match that exactly, then we're just going to explode the bomb. So at least we can see that. And if we go to our logic here, we can kind of understand this as well. Get the input, read line, put that into this function, scan it, make sure it matches. If it doesn't, then just explode it. So let's just keep going. This is something interesting too. Add RAX to RCX. Okay. Explode bomb. Compare. RBP plus 4 to 5. And then we have an XOR here. Okay. Compare this to 7. Okay, so I'm just looking at things randomly. Let's just continue on, and let's just go into the code. And so again, just stepping through. Just stepping through here. I'm just a renegade hockey mom. That should be okay. And then this is the powers of 2. Go in here. Okay. Now we know we need 2 numbers. Let's just do 1, 2. And let's just step through here. And we're just going to go line by line. At least past this first section here. So at least we seem like we understand everything from here so far. It doesn't seem like there's an issue here, just allocating information. It doesn't seem like anything is super significant except this where we're reading the input. But once we get here, let's just continue on to the jump part, where it jumps here. Okay. Loading some value into EAX. RBP plus 4. Okay. So when I saw that, EAX is now 1. EX equals 1. So this makes me think, is this my input? From here, after I executed this line, I'm not sure. I'm just going to keep going. RBP plus EAX, put that into this value. Okay. And so there's another movement here. I move that from here to here, move this into here. So let's check what's at this memory location, RBP plus 134H. RBP plus 134H. And let's load it as a hexadecimal value. Okay. I don't see anything super interesting yet. We put 1 into that value because there wasn't anything significant there. Compare it with 7. Jump if it's above that value. Okay, I see. Compare it with 7. Jump if it's above 0 FA. Oh, it's going to explode. I see. So I'm guessing that if the input is greater than 7, then it'll explode. So we're going to just write that just as an assumption right now. So I guess like int 2 equals input if int 0 is greater than 7, and then we're just going to say explode bomb right now. I don't know if that's going to be exactly the case, but this seems like the jump thus far. Jump. Okay. Move that value. Yeah. Move it back into RAX. Yeah. So we're right again. We didn't jump here. So we're actually right back here. We didn't jump, so we're now in this line of code. Putting that value that was actually here, putting it back into RAX. Loading this into RCX, this address. Loading this into RCX. Huh. Move this into EAX. Okay. There's something that's happening here that seems pretty significant, especially if you look at this line here. Anytime you see kind of like this multiplying by 4 or multiplying by this bytes, it's kind of like going through an array of information, or at least this is what I'm assuming. It's going through RAX, which times 4, which is meaning that it's indexed by 4 bytes, meaning it's probably indicating compare 7, 134, yeah. This seems like the first input. This gets loaded into RAX. This value is traversing here. Okay, but let's just continue on into the debugger before we do anything else, because we're exactly right here in our logic. So right now we're right here. And so let's just continue on before I make any other assumptions. But let's just write some stuff down here. So this seems like if I compare this line and this line, it does seem like there is some sort of indexing involved with first input, like 1 to 7, 1 to 6, I think, right? 1 to 7. Jump if above. I think it's like 1 to 7. But let me just make sure. RCX. Now it makes me think that this address is going to point to something specifically, to the beginning of some index here that we're, or not, the beginning of some collection of a significant, like an array. It's going to the start of an array. So this is the address. I feel like it's an array of integers times 4 bytes, 4, yeah. Or 4 bytes is just the hexadecimal where it's located. But this is all that I know thus far. Evolve with the first input. RCX here must be start of some array or collection of data. and then RAX. RAX indicates some index or some sort of traversal. And it's not the RAX. Again, we're looking at that first input. So the first input indicates some sort of traversal in some array collection via index. Okay, so the first input we had was 1. So let's just go ahead. RCX points to this location. And then we're just going to write that here. RCX specifically equals that. If I pull this information right now from our memory location, what do we have here? 1, 2, 3, 4, 5, 6, 7. Okay. Let's just pull this. So right now, hold on a second. 1, 2, 3, 4, 5, 6, 7. Okay. This is, let me just copy this part too. Okay. So at that specific location, and this is just the memory, address, so it's the same thing as this. Less than 7 here. Compare it with 7 if it's above 7. So we can actually see that this matches 1, 2, 3, 4, 5, 6, 7. And so that does seem pretty significant. Load this address. At this address, we have this specific information here. Now we're going to go and load it to EAX with our input is equal to 1 here. So this should be, from what our hypothesis is, exactly where we're moving to EAX. And so I hope I'm right. 1, 2, 2, 4, 5. Oh, that is so wrong. Oh, maybe because I'm not looking at, I should look at this one. Sorry. I need to look at this address. I am tripping. Let's see, what do we have here? And we'll just do 1 here. Okay. Okay, we have something completely different now. Okay. 0, 1, 2, 3, 4, 5, 6, 7. Okay. Sorry. I'm looking at the wrong location. This is loading into that address, but this is actually more significant. It seems like, because once I loaded, once I had the input as 1, RAX is equal to 1, 2, 2, 4, 5. And so we can kind of see that this is kind of like pulling the address here, RAX, that index, to these values here. So it indicates some sort of traversal in some sort of way from the first input. Our first input was 1. Load this into RAX. Add RAX and RCX. And so we have some relationship now. RAX equals RAX plus RCX. What does that mean? What does that do for us? Oh, well, okay. So we jump to that new location, wherever that is. So this plus something here is going to equal the location that we're going to jump to. So location to jump to. Okay. And why is that significant? So let's see. Right now we have 2, 2, 4, 5. So we have this. Add together. It's just going to be 7, 7, F, 6, 1, 6, 1, 7, 2, 2, 4, 5. I think that's right. I'm going to go ahead and see if I did that right. RAX. Yeah, that's right. What does that mean? Oh, okay. Actually, it matches the addresses here. 72245 matches 72245. 72245. Am I going the wrong way? Oh, I'm not even seeing it. Sorry. Let me just redo this. Phase 3. Am I getting all the information now? No. I'm missing something. Okay. I think what's crucial, jump to that value. Okay. I should copy and paste as much as I can here. And I'm going to just copy and paste here. Is that where I should copy and paste? Yeah. Let's see if I can get more of this. 447E 544 6A. Yeah. Let's see how much more I can copy and paste here. Sorry, just going to keep getting this one as well. Let's see if I can copy and paste this. Okay. I just want to see if I can find this specific address because it actually goes here. Goes here for what reason? Okay. We're in some belly of the beast type stuff here because this seems like a lot of stuff going on at the moment. So what would be useful is seeing how much I can copy and paste. 9B. Give me 1 second, sorry. Phase 3, RP plus 44. AX phase 3. Okay, I see. We're going to have to try and get this right here. Yeah. This is the last part that we need to look at. Okay. I think I got all the code here. Whew. Okay, so this seems like a lot of individual logic here. So let's just look back up here. This is an index of different different values that we take into here, jump to some location here. So the first value was 1. Go here. From here, we have a whole bunch of different things going on here, like add 274 hexadecimal. We have a subtract from the same. Okay, so this is also interesting. They're all to EAX. Move RBP plus 44. What's an RBP plus 44? RBP plus 44? Is that significant? Huh, this is 0. Starts at 0? Starts at 0? I didn't put a 0. I put a 1 and a 2. Our input was 1, 1, 2. So this 0 is what's here. Put that in here. Put that in here. So it's always constantly doing some addition or something to that. Move EAX here. Subtract here. Okay. Let's just move out. EX. Always on the same value here. EX. So it seems as though... Is this significant? Let's just continue on. Going here. Going here. Ooh, going here. Going here, going here. Okay. Compare RBP plus 4 with 5. RBP plus 4, I swear, was our first input. Is that our first input? RBP plus 4? Yeah. RBP plus 4. Compare here. What does that mean? Compare our first input with 5? Compare our first input with 5. If it's greater than that, go to this address. Jump to 122. Is it 90? Oh, this is bad. Explode. Okay. Huh. Jump if it's equal. Jump if it's equal. Jump to this address, A2. Did I write that? Maybe I wrote something wrong here. A2. No. Okay. Let's just notice that we have some comparisons here with some jumps. Compare RBP plus 44. I'm comparing what I had here. I'm doing something to all of these. I'm doing some number. It's constantly going through some adding, subtracting, adding, subtracting. Yeah. Jump. If I get here, I jump. Compare this with 5. Okay, this is happening 2 times. Compare it with 5 here. So we have a compare with the first one. Jump if it's greater than this. 9D. 9D. Is that right? 17229. Yeah. I feel like this is saying don't be bigger than 5. So there's some constant coordination for this not to be, if it's greater than 7, it'll explode. If that value is greater than 5, explode. That happens 2 times. So we can see that if, compare it with here, if it's greater than that value, then explode. Go down here. If it's greater than that value, explode. So let's just see. We're right at the end at this point. So this last jump, compare and jump, must mean that this is pretty much like the last hurdle that you have to do. 2A2. Okay. If this is equal to this, EAX, so one of these is probably like the final solution of all of the calculations are happening here. Once we get to that, if they are equal to one another, then we can jump and just finish up this logic here. And so we won't explode the bomb. So this has to be equal for it to finish. This is like the massive amount of calculations, okay? Compared to some value. So we don't know, right? Let's just go back up here because this seems like significant because we got this here when we added this to this. Jump to this value here, and so now we're starting with a subtract. So subtract, and again, we can make this a little easier by going to the calculator, and let's just go ahead and let's load up what these values are in decimal form or base 10. And so 274, which would be 628. So plus 628 minus 24C. Let's see, 24C, 588 minus 588, 280. 280, 640. 2B0. Oh, B, not 8. 2B0 is 688 plus 688. Okay, we're going here. 7E. 7E, 126 minus 126. Plus 126 minus 126. Okay. Plus 126. Okay. Minus 126. So there is something going on here that's interesting to me. There's a lot of 126s here that make this just scream at me that this is something to pay attention to. Let's look at what the possible addresses would be if we added them together with this value here, just to see where the locations would arise. So again, 616.17223A. That would be if this was 0, if this was 1. If 7FF616.1722250, this is if it's 2. FF61617 going to 3. 225B is 3. 7FF616172264 is if it's 4. And we seem like we're limited to 5. So we don't really even need to think about these last two values. We just can look at this as our last value. 616.122.6. Oh, I did this wrong. Sorry. 17226D is 5. So we have these different addresses we're jumping to. Let's see. This is where jump if 0. If the first input was 0, go here. This one was jump if 1. So I'm just going to add just some space here just so it's not so condensed. This one is 2. Jump if 2. 225B. 225B. Jump if 3. 225B. And then we go here. 2264. Jump if 4. And then we're going to 226D. Jump if 5. Okay. So these are the only places that we can jump to. Now we have a lot of information so far, but let's just keep going because we're not 100% certain on this value here. We're still just guessing. So let's just keep going here and stepping through. And so we have all of this. Calculations are going on. It's continuously adding to RAX. And so once we finish, we're going to go to this compare value. And let's just go here. It seems like it's the same input. And that's because it is. And it would be wise to just test it on your own with some other inputs. I'm not going to go test it because I've done it personally, but just reassessing your hypothesis, like maybe you don't know for sure. Maybe you want to switch the first input. And so we know that the first input is restricted in the logic between 7. It can't be bigger than 7, and it also can't be bigger than 5. So it has to be 0 to 5 between these jump calls. We know it has to jump between these values. And so what is going to be the most important step here? Jump if compare. And so now I got to this part here, and I noticed something interesting here. RBP plus 44, if you just continue to go through it, loads up into this value here. So this is RBF, the base pointer plus 44H, that's memory here. EAX now is 2. So RAX is 2. Then this must mean, just from what I'm guessing, is that the second input must match the calculations made from the jumps. Meaning, if we jump at the right place, we can kind of predetermine what this value will be. Starting with the assumption that we're starting from this 0 value, adding, subtracting, adding. And so the first input here will take us to some location here, jump to that specific location here, make sure that we're doing the right number of calculations because we're going to keep sequentially going down. And then finally, whatever the second input is, we can match it with our second, or sorry, the second input should match here what happened after all of the calculations that are going on. So this could be a lot of math, or we can actually just start from the bottom up. Because we know that these calculations have to be made. These two instantly cancel each other out. So that's just 0. If we jump here, maybe we can notice that it's minus 126. So minus 126 what? We don't know. Maybe we can jump here and we know that this value is 126, negative 126. So we can kind of use that as the second value. But what I did is I just knew that if I jump here, these two will cancel each other out. These two cancel each other out. And so jumping at the value of 4 will actually give us the value of 0. And so we can just continue on here. Because this one doesn't work. Yeah, but again, I have some hypothesis. I'm just going to test this out because I don't want to step through. And sometimes you don't want to just go through again and again because you kind of know that, hey, I'm at the last part. I'm thinking that it's going to be that as the answer. And so let's see. I am just a renegade hockey mom. 4, 8, 12. 1, 2, 4, 8, 16, 32. Is it 40? Okay. That was the answer here. So that was correct. So let's just break down the logic here. How is this correct? We have some value here. We have some list of addresses here. So this is probably like a go-to statement. Go to some address, right? We'll put a star here. Address. And it's probably a list of different calculations like adding, let's say n is 0, right? N plus or equal to 126. Let's see. What is the math we had? N plus 126, 268 minus 588. So it seems like there's an assortment of different n minus 628 minus equals 588. And so if we go to the right location, go to this, go to this, A addresses 7. So we have a collection of addresses here. And they're instantiated with like different values. Address equals, or sorry, address is this value here. It's like some address location. We have an array of different values. I don't know how to represent this. I'd probably say this is like maybe an integer. It's like a hexadecimal value. Hex of 7 is equal to some value here. Values. We're adding those values to the address. Address equals plus or equals that hex int 0 value. From that value, we're going to have some lists of, so you go to that address, and then we're going to just go through those calculations. Once we go through those calculations, we have to see if that int1 is equal to n. If it's not equal to n, then we would explode bomb. And so since there was a strange pattern of n minus equals 128, go to n plus equals 128, go to n minus 128, go to n plus 128. I noticed that there was this pattern here. Jump to the right place. All these cancel out, so I just assumed that this one would be 0. So it's not a very thorough explanation of exactly what the code is doing because on the top of my head, I don't exactly remember how we can represent the address location. But there is actually some pointer manipulation and addition going into this, going to that specific address, because at that specific address, it's going to perform some calculation. Once we do that, check the second input and see if that matches the value after all those calculations have been performed. Now, I don't think for certain it has to be a 0, but I think if you don't do 4, 0, you just have to make sure the math adds up. I didn't try it with any other value, but after I solved this, I just left it as that. So that was just kind of like my thought process going through this. I hope that was very helpful. And again, another shout out to Dr. Gorgon. I don't think I would be able to solve it. I was stuck a lot at this portion, but once I started to understand that it is this hex value adding to that address location, that started to make more sense. So, all right, well, thank you. I hope this video was helpful. I hope you enjoyed it, and that will be it.